Hello students, welcome to my YouTube channel. In this lecture, I am going to answer questions from sample paper number 6, RK Bali navigation book. So let's start. Question number 81. A remote indicating compass has less deviation than a normal compass on the top of the cockpit panel because it is carrying a well-damped floating magnet. It is normally mounted in a part of the plane where magnetic interference is minimal. It receives a higher flux density from the Earth's magnetic field. So correct option is option Bravo. This is the main advantage of a remote indicating compass. It is not located in the cockpit where electrical influences are very high, but located away from that, located away at a place where this interference from electrical influences will be as minimum as possible. So option Bravo is the correct answer. Do read magnetism chapter from R.K. Bali very well, thoroughly. Question number 82. The use of TCAS, Traffic Collision Avoidance System, for avoiding aircraft in flight is now general. Okay, everyone uses it. TCAS uses for its operation what? The ECOS of collision avoidance radar system installed on board, both the replies from the transponders of aircraft and the ground-based radar, the replies from the transponders of other aircraft. So the correct option here is option Charlie. TCAS works independently of any ground radar. That is one very first very important point. Second, TCAS meets transponder equipped aircraft. Need transponder equipped aircraft. So let's say this is your aircraft here. Your aircraft has a transponder. Around this aircraft there will be first inner bubble called warning area or collision area, and the outer bubble called caution area. If any plane, if any traffic penetrates the outer bubble, let's say here, okay, outer bubble, so your aircraft will generate traffic advisory. If this aircraft continues its forward movement and enters the inner bubble called warning area or collision area, your TCAS will generate resolution advisory. It will generate a resolution advisory. In order to use this facilities of TCAS, traffic advisory, resolution advisory, the traffic around you must have a transponder. Must have a transponder. It must have a transponder. If the traffic has mode C transponder, so you will get to see relative height between your aircraft and this aircraft. Okay, so let's say you're flying at 1000 feet and that aircraft which is coming head on is flying at 800 feet. So the relative altitude between your aircraft and that particular traffic aircraft is minus 200, means that traffic is minus 200 feet below you. If the air traffic which is coming head on in front of you has mode S transponder and your aircraft is also equipped with mode S transponder, then resolution advisories of both your aircraft and that traffic aircraft will be coordinated. Will be coordinated. That means if your aircraft receives a climb resolution advisory, this traffic aircraft will receive a descent resolution advisory. So both resolution advices are coordinated. If one gets a climb command, the other will get a descent command. So all this operation of TCAS is based on secondary radar. The transponder in this aircraft, okay, the transponder in this aircraft will transmit radio pulses in the direction of the traffic. Okay, in the direction of the traffic, the transponder in this particular aircraft, this traffic aircraft, okay, it will reply to this interrogation pulses and send reception pulses back to the transponder aircraft. So interrogation pulses are sent, they are replied and sent back to the original aircraft or interrogator aircraft. So the correct answer here is Charlie. The replies from the transponders of other aircraft. Echoes of collision avoidance radar system especially installed on board. So this is very irrelevant. Echoes are primarily used in primary radar system, not secondary radar. And here Bravo is eliminated because in TCAS there is no work for or there is no use for ground-based radar. So option Bravo is also eliminated. Airborne weather radar works in super high frequency band. Now airborne weather radars operates in at a frequency of 9.375 gigahertz. So between 9 and 10 gigahertz. So in this super high frequency band. Why? Large water drops and storms give good reflections at 3 centimeter because the frequency or the wavelength corresponding to this particular frequency is around 3 centimeter. And small drops like fog and mist do not give reflections. Enable the equipment to be powerful to receive reflection from large water drops and dust storm. So the correct option here is option A. Now airborne weather radar uses this particular frequency of 9.375 gigahertz and wavelength of 3 centimeter because let's say here is a cloud. There are large water droplets in this cloud as well as some small water droplets. So airborne weather radar is invented to detect turbulence, but it cannot detect turbulence directly. So it first detects large water droplets suspended in the cloud. When it detects these large water droplets, then with the help of that information, it can indirectly tell you whether there is turbulence present in that particular cloud or not. So you first directly detect cloud droplets or large water droplets, and then from that information, you derive a supplementary or secondary information of turbulence information. Now, large water droplets are always a characteristic feature of clouds of vertical development like cumulus clouds, CB clouds, like that. But small water droplets are often not indicative or are not indicative of strong turbulence. So small water droplets can be ignored, and majority of times small water droplets are suspended in clouds which are not a threat to aviation safety. Low level clouds, medium level clouds, very low level clouds like fog. So you can completely ignore them. What you are concerned about is large water droplets because these large water droplets are often found or spotted in clouds of vertical development. And clouds of vertical development have updrafts and downdrafts. These updrafts are going to suspend these large water droplets in the atmosphere for a long period of time. So if you detect these large water droplets, that means indirectly there are updrafts in that particular airspace or in that particular cloud region. And this updrafts means this cloud will be vertically developing into a CB cloud. Correct? So a wavelength of 3 centimeter, when you send a wavelength of 3 centimeter, this 3 centimeter wavelength will strike this large water droplet and get reflected back at the airborne weather radar receiver in your aircraft. If there is a small water droplet like this two small water droplets, so in that case, this 3 centimeter wavelength radar signal will penetrate the small water droplets and go beyond the cloud, go beyond them. Okay, so you will not get a reflection from small water droplets because that is useless, irrelevant to our aviation safety. What we are concerned about is getting reflection from large water droplets, and this particular wavelength achieves that purpose, achieves that goal. So we are using 3 centimeter wavelength. Always remember that The size of the water droplet and the wavelength of the signal these two things are going to determine whether the radar signal is going to get echoed or reflected or not. If the size of the water droplet is too small, then this wavelength signal will penetrate that cloud layer and go beyond it. If the size of the water droplets is somewhere around or equal to the wavelength of the signal, then reflection will happen successfully. So correct option is option alpha. Next, do watch my airborne weather radar videos. I have solved all questions of airborne weather radar from Oxford Radio Nav, Heath Williams, as well as a book called Ground Studies for Pilots by R.B. Underdown. So I have done all the back questions. Watch those lectures. Your concepts will be more refined. Question number 84. You are flying at a flight level of 200, means aircraft is flying at a level or altitude to 20,000 feet, flight level 200, at a range of 60 nautical miles. You have deflected your radar beam plus 1 degree up, minus 4 degree down. What is the height of this cloud? So you have to find the base of the cloud and the top of the cloud. So let's say you're flying at flight level, you're flying at flight level 200, that is 20,000 feet. You're flying at a flight level of 200. Okay, there is a cloud in front of you that is 60 nautical miles, 60 nautical miles away. You have to find the height of the top of this cloud and the base. Okay, height and the base. Now the formula that you are going to use is top of the cloud is equal to tilt minus beam width divided by 2 multiplied by range multiplied by 100. So tilt is plus 1 degree, beam width is 4 degree, range is 60 into 100. So 1 minus 2 into 6000. So minus 1 into 6000. That is minus 6000 feet. So that means the top of this cloud is 6000 feet below you. Okay, so 6000 feet below you means flight level is 20,000 feet. Cloud is 6000 feet below you. So 20,000 minus 6000 is equal to 14,000. So the height of this cloud or the top of the cloud is at 14,000 feet. So the only option here is option Charlie. So you are going to select that option. And the base of the cloud is 8,000 feet. You can also calculate the base of the cloud using the same formula here. So instead of writing tilt 1 degree, you are going to put the value tilt 4 degree in place of that. So you will get 8,000 feet as your answer. Next, question 85. Conical pencil beam of a weather radar is 5 degrees and the beam is tilted 4 degrees up. So tilt is 4 degree up, beam width is 5 degrees. The top of the cloud at 70 nautical miles away. You have to find out the top of the cloud. Okay, so again, use the formula tilt minus beam width by 2 into range into 100. So tilt is 4 degrees up, beam width is 5 degrees, range is 70 into 100. So 4 minus 2.5 into 7,000. So 1.5 into 7,000 is 10,500. Okay, that means What is the approximate height of the cloud top above the aircraft altitude? It is 70 into 100 tilt 4 degrees up. So 4 minus 2.5 is 1.5. So it is 10,500 feet above you. So the closest option here is 9,400, 11,100. So 10, so 11,100. So it is better to select option Charlie. 11,100 and 10,500, the difference is 600. But the difference between 9,400 and 10,500 is 1,100. So the closest difference is Charlie. So select that option. Question number 86. The transponder ident button is used for what purpose? Or initial contact with ATC, when requested by ATC, when changing codes. So ident button is used only and only when requested by ATC. Now look, this is the ident button here. This is the ident button on your transponder. Now this ident button is pressed only and only on the request or instruction given by ATC. Now when you press this ident button, the radar blip corresponding to your aircraft position in the sky will flash for 20 seconds. It will flash for 20 seconds. So this is the uh, radar screen of your ATC controller, and on this radar screen there will be many radar blips belonging to many different aircraft which are flying in the airspace under the supervision or under control of this particular air traffic controller. So whenever ATC wants to identify your aircraft, okay, out of so many aircraft on its radar screen, there are three ways he can identify you. He can ask you to turn left heading or turn right heading. So when you do that or execute that particular turn, let's say to the left hand side, so the radar blip corresponding to your aircraft position in the sky will also start turning to the left hand side or to the right hand side as requested by ATC. So that is how ATC will come to know that yes, this particular radar blip is belonging to your aircraft. Second way is ATC can ask you to give VOR and DME information. That means the radial you are situated on and the distance you are situated, the distance you are at. For example, let's say this is your VOR DME station and you are situated on radial 090. Now radial 090 is unlimited in length. Okay, so if I say I'm on radial 090, that means I can be here, here, anywhere on radial 090. But when I say I am on radial 090, 20 nautical miles away from the station, that means I get an accurate pinpoint position. Radial 090, 20 nautical miles away. So that means I am here, somewhere here. So that is second way. And the third way is ident button on your transponder. So when you press that ident button, the radar blip starts flashing for 20 seconds. So do watch all my secondary surveillance radar video lectures that I have already uploaded from Oxford, Keith Williams, Ground Studies for Pilots. So in that I have explained these concepts many times. So pay attention, ident button can only be pressed only and only when requested by ATC. If you pressed without ATC's instruction or without ATC's knowledge, so that will be a very big mistake or safety issue, meaning ATC controller might have asked some other aircraft to press his ident button. Okay, and if you press your ident button at the same time, so the radar blip corresponding to your aircraft will flash on the ATC's radar screen. But ATC will mistake this particular flashing of radar blip for aircraft corresponding for aircraft for another aircraft to which it originally asked to press the ident button. So never do this mistake and always press the ident button only and only when requested by ATC. Question 87. Airfield surveillance radar. is required to operate at a minimum range of 0.125 nautical miles. What is the maximum pulse width of the transmission? So always remember, minimum ranges of radar depend on the pulse width, and maximum range of a radar depend on pulse recurrence frequency, PRF. So now here we have to find out the minimum range. So minimum range formula is pulse width multiplied by speed of light multiplied by speed of light divided by 2. So here pulse width, here minimum range is given to you 0.125 nautical mile. Convert that into meter. So 1852 meters, right? Pulse width x, speed of light 3 into 10 raised to 8 meter per second divided by 2. So x equals to 2 into 1852 into 0.125 divided by 3 into 10 raised to 8. Correct? So x will be 2 multiplied by 1852 into 0.125 divided by 3. So 154 divided by 10 raised to 8 seconds. Now pulse width is always in microseconds, right? So you are going to multiply this by 10 raised to 6 into 10 raised to minus 8 microsecond. So pulse width is going to be 154 multiplied by 10 raised to minus 2 microseconds, which is 1.54 microseconds. Now, okay, towards a stationary transmitter measures a frequency shift of 2015 hertz, okay, and transmitted frequency is 4.75 gigahertz. What is the speed of this aircraft? So here is your aircraft. It is transmitting this at frequency of 4.75 gigahertz. Doppler shift is 2015 hertz. We have to find out velocity. The formula is Doppler shift is equal to velocity divided by wavelength. Okay. Now we must first find wavelength. Now wavelength is speed divided by frequency. Speed is 3 into 10 raised to 8 meter per second. Frequency is 4.75 gigahertz. So multiply that by 10 raised to 9 hertz. Now 3 divided by 4.75 is 0.63 into 10 raised to 8 divided by 10 raised to 9 meter. So 0.63 divided by 10 meter. So 0.063 meter. Correct? So substitute here velocity divided by 0.063, okay, is equal to 2015 hertz Doppler shift. So velocity is 2015 multiplied by 0.063 meter. So final answer will be 2015 0.06 126.9, that is 127 meter per second. Now 1 knot is equal to 0.515 meter per second. So 127 meter per second will be equal to how many knots? So 127 divided by 0.515. So 127 divided by 0.515 is 246 knots. So the correct option here is option Bravo. Question 89. Airborne weather radar has following characteristics: wavelength, pulse width, frequency given. what is minimum range of the radar, right? So minimum range of the radar depends on pulse width. Maximum range depends on frequency. So minimum range equals to pulse width multiplied by speed of light divided by 2. So 2.2 microseconds multiplied by 10 raised to minus 6 to convert that into seconds, okay? Into speed of light 3 into 10 raised to 8 meter per second divided by 2. So range will be equal to 3.3 into 10 raised to 2. So range is 330 meter. Correct option is option A. Simple formula based. Last question. The time taken for the transmission of an interrogation pulse by a DME to travel to the ground and return is 2000 microseconds. What is the slant range? So the range from airborne weather radar, correction, the range from ground station to aircraft, one way distance is equal to speed of light into time divided by 2. So 3 into 10 raised to 8 multiplied by time. Now here the time taken is 2000 microseconds. Now if you know the DME theory very well, you will know that when aircraft interrogator transmits interrogation pulses, the ground receiver or the ground station is going to accept that pulses, wait for 50 microseconds and then retransmit the pulses towards aircraft. So this 2000 microseconds is inclusive of 50 microseconds. So we are going to subtract 50 from this. So the actual time to go and come back will be, ignoring the delay, 2000 minus 50, 1950 microseconds multiplied by 10 raised to minus 6 seconds divided by 2. So 1.5 into 1950 is 2925 into 10 raised to 2. So 292.5, this is 2925 into 10 raised to 2 meter, which is equal to 292.5 kilometer, which is equal to divided by 1.85, 158 nautical mile. So the correct option here is option alpha. Simple. Do watch all my DME lectures. I have solved all the back questions from DME, Keith Williams, Radio Nav, and Oxford Radio Nav. So do watch that. So with this, I'll stop here. I will do the last 10 questions in my next video lecture. I hope and expect that you have understood all the 10 questions that I answered in this video lecture and explained it to you all. If you have any doubts, comments, feedback, let me know in the comment box of this video lecture. I'll see you next time. Thank you.